Polyvagal theory, a science of safety. This was printed in Frontiers in Integrative Neuroscience, published May 10th, 2022, and written by Dr. Stephen Porges. Clinical implications. From a polyvagal perspective, it may be helpful to investigate how challenges move us into physiological states of threat that would disrupt our connectedness and place our mental and physical health at risk. But more relevant to both clients and personal survival, therapists need to identify and emphasize the innate resources that clients have available to mitigate the potentially devastating reactions to threat, which in turn can destabilize the autonomic nervous system, sometimes resulting in visceral organ dysfunction and compromised mental health. Awareness of the neural systems underlying polyvagal theory informs both therapists and clients regarding the threats to survival that can shift autonomic state, moving it through sequential neural platforms or states that mimic evolution in reverse or dissolution. Functionally, to inhibit the trajectory of dissolution to calm, we must first use the competence of our social engagement system, a uniquely mammalian myelinated vagal pathway involving brainstem structures, regulating vocal intonation and facial expressions, to connect with others and calm our physiology. Without these resources, we are vulnerable to move into adaptive defensive states. Our defense repertoire is first expressed as chronic mobilization, requiring activation of the sympathetic nervous system, and then expressed as immobilization, which is controlled as an evolutionary, older, unmyelinated vagal pathway. In the absence of an active social engagement system, the mobilized state provides an efficient neural platform for fight and flight behaviors. For many individuals, this state will reflect chronic anxiety or irritability. When mobilization does not successfully move the individual into a safe context, then there is the possibility that the nervous system will shift into an immobilized state. Immobilization with fear can be associated with features of death feigning, syncope, the disassociation, withdrawal, loss of purpose, social isolation, despair, and depression. Although both defense strategies have adaptive values in protecting the individual, they are dependent on different neural pathways. Example, high sympathetic tone or high dorsal vagal tone. Activation of these systems, independently or simultaneously, will interfere with interpersonal interactions, co-regulation, accessibility, trust, and feeling safe with another person. Thus, defensive states emerge from neural platforms that evolved to defend, while simultaneously comprising capacities to downregulate our defenses through the co-regulation with a safe and trusted individual. Basically, the theory emphasizes that in the presence of cues of safety, which we associate with positive social interactions, the mammalian social engagement system can down-regulate our innate reaction to threat, whether the threat is tangible or observable or imagined and invisible. Stress and threat have a common neurophysiological physiological foundation. Several years ago, I wrote a paper on stress and tried to unravel the ambiguity of the term, especially the circularity of using stress as both a stimulus and a response. Now, after almost 30 years seeing the world through a polyvagal perspective, I have written about safety and threat. I'm reminded about my earlier approach to operationally defined stress. It's easy to understand that the use of stress as a construct is ambiguous, since stress has been operationalized as a response as well as the contextual trigger producing the response. As this circularity is disentangled, note that the concept of threat has a scientific history similar to stress, in which removal of stress is conceptualized as optimal, and removal of threat is assumed to produce feelings of safety. Both constructs focus on the negative attribution of potentially observable and quantifiable features, influencing biobehavioral processes while originating outside of the body. Moreover, neither construct elaborates on the mechanism that would optimize function following the removal of stress or threat, which implicitly assuming that removal is sufficient. A polyvagal perspective shifts the discussion from the external features defining stress and threat to the nervous system's ability to support or disrupt homeostatic functions. Example, processes supporting health, growth, and restoration. This new conceptualization would redefine stress as a measurable state during which homeostatic functions are disrupted. A redefinition would be consistent with the distinction between stress and coping by emphasizing that coping would functionally include an autonomic feature enabling a return to homeostatic function. It would also refine the dialogue distinguishing between good and bad stress from the stimulus to the response. Thus, similar to threat, stress results in a retuned autonomic bodily processes. If we assume that removal of stress and threat have the same autonomic signature, in which autonomic state is disrupted, and metabolic resources are diverted from homeostatic functions to survival needs. We could succinctly propose that feelings of safety would describe recovery to both stress and threat, since feelings of safety are dependent on a return to an autonomic state that would support homeostatic function. The ability to move following a challenge into an autonomic state that supports feelings of safety could also operationally define resilience. Consistent with Cartesian dualism, there's an inherent acceptance that the external disruptor, example the stressor, could be operationalized and reliably result in a measurable stress response. In the 1985 paper, I challenged the prevalent SR model, which had been fundamental to experimental science, with an SOR model in which the O, or organismic state, measured by autonomic nervous system indices, would function as an intervening variable, mediating or moderating the influence of S on the R. Note that the SR model is a behavioral restatement of the cause and effect relationship that has served as the basis of empirical science's quest for laws of nature. Because the intervening variable is assumed to be a source of response variability, researchers within the experimental laboratory-based disciplines are often uncomfortable and seek reassurance in comparatively simple interventions that are relatively independent of the individual differences associated with organismic variables. Among examples of this approach are manipulations of neural blockages, powerful drugs that block specific neural pathways, the surgical severing of neural pathways, or brain lesions, ablating specific areas of the brain. These manipulations are powerful, and the impact on all participants is relatively similar. In the analysis of manipulation studies, statistical significance is driven by the relative change to the manipulation versus the individual variations in response parameters among subjects. With powerful interventions, strong relationships are easily observed and statistically confirmed. In contrast, using the SOR model, consistent with the polyvagal perspective, we're looking for an interaction that will inform us about the features that distinguish between those that have strong or weak responses to the same manipulations. In interpreting interactions with autonomic state on the parameters of the R, there's often a discomfort within the experimental laboratory-based sciences. Thus, reporting interactions with state variables may provoke criticisms that the findings were due to a faulty hypothesis, poor experimental control, inappropriate study design, or a yet-to-be-identified variable influencing the gradation of reactivity. Frequently, an alternative plausible explanation that the response effect is not detrimentally related to the stimulus, example the cause, and is not entertained. Fortunately, with the advent of robust multivariate statistical models, now there are accepted techniques that enable researchers to evaluate how other variables may indirectly, via intervening variables, mediate and moderate cause and effect relationships. These quantitative techniques were not commonly available during the early part of his research career. Here is the introductory segment of the 1985 paper. The construct of stress has a variety of definitions. Often the definitions appear circular since stress has been defined in terms of environmental stimuli. Example, a stressing environment. As an organismic vulnerability, a stress-prone organism, and a response to the environment. Example, a stress response. The inherent circularity of the definition has limited the succinct articulation of what stress is and what causes it. Even if stress was operationally defined by labeling the stressing stimulus as the stressor and the behavioral and physiological response or adaptation to the stressor as stress, at least two problems would remain. One, the definitions of stress and stressor would be circular, and two, there would be situations in which the individual and the state variable mediate and modulate the degree of responsivity and adaptability. Example, stress of an organism to constant environmental manipulations. Example, stressor. For example, the same environmental conditions that may result in physiological debilitation for one subject may not produce a discernible behavioral or physiological response to another subject, or even in the same subject tested a second time. Thus, stress must be conceptualized not only in terms of the stressor, but the observed response, but also in terms of the physiological state or vulnerability of the organism at the time of the exposure to the stressor. One approach to the complex problems associated with stress research would be to reformulate the research strategy. Research is generally conducted within the framework of a mechanistic stimulus response model, SR. In this model, the response variable is assumed to be determined by the stimulus variance. Thus, stress response would be determined primarily by the stressor, and as noted above, the characteristics of an organism at the time of the experimental manipulation would contribute to the manifestation of the stress response. Therefore, it would be expedient to use research designs that would enable the examination of the stress response, not solely as the product of the stressor, but also in terms of the state or condition of the organism prior to the stressor. The research would be formulated within the framework of a stimulus-organism response, SOR model. Thus, the changing characteristics of the organism might index vulnerability to the stressor and determine the degree to which the individual would experience stress. As we discuss stress, we note that the experience of stress and threat appear to reflect a common neurophysiological platform. Substituting threat for stress in the above paragraphs would result in similar conclusions, and stress similar to threat would objectively be defined as a disruption in homeostatic function. Basically, stress is triggering a bodily state of threat and reorganizing the autonomic nervous system to promote survival. Using this definition, we'd be able to decouple good and bad stress as being defined by the duration and the consequences of the disruptions. Short disruptions or acute stress followed by rapid recoveries would function as neuro exercises promoting resilience, while more chronic disruptions without periods of recovery would lead to disease and tissue organ damage. Research on perceived stress and coping that focuses on coping and the link between coping and positive emotions would be consistent with polyvagal theory's emphasis on an operational definition of a stress response as prolonged disruption of homeostatic function and the powerful influence of cues of safety in downregulating threat. A problem with using either threat or stress is that both constructs lead to binary either-or models, in which removal of threat would be sufficient to feel safe and removal of stress would be sufficient to optimize homeostatic function and relaxation. Missing is an acknowledgement of the nervous system's need for cues of safety and connectedness. These models would be reconceptualized to incorporate an understanding of safety and optimal homeostatic functions, which might lead to operationally defined neurophysiological-based measures of recovery and resilience. Others have proposed relationships between safety and stress that focus on constructs previously explored by the polyvagal theory. For example, the relationship between safety and stress forms the basis for the generalized unsafety theory of stress, proposed by Branchcott and others in 2017. Although the two theories use different terms and constructs, the two theories can be contrasted if we assume that stress and threat responses are equivalent. The initial principle proposed emphasizes that the stress response is a default response. In contrast, polyvagal theory proposes that stress is due to the disinhibition of a safety state and is not a default state. In fact, polyvagal theory would propose that stress, example, threat reactivity, rather than being a default state, can be reflected in two defensive states that would compromise homeostatic functions. The defensive states adaptively require foundational, survival-oriented, autonomic states that differ from the safe state that supports homeostasis. To shift states, polyvagal theory proposes a process of dissolution, triggered by a neuroception of threat that results in the disinhibition of evolutionary older neural pathways that compromise homeostatic functions to serve foundational survival needs. By invoking the Jacksonian principle of dissolution, polyvagal theory proposes that stress is an adaptive product of the disinhibition of a safety circuit that supports homeostatic functions. This disinhibition will occur when survival is challenged by cues of safety, which trigger via neuroception the autonomic nervous system into states of defense. By acknowledging a hierarchy of autonomic states that parallel vertebrate evolution, the theory proposes a dissolution sequence in which more ancient autonomic circuits become available for defense. The critical points are: 1. Stress is not a default state, but a disinhibition of older survival circuits, resulting in shifting the autonomic nervous system into states of defense. 2. Autonomic state mediates the behavioral and physiological features of stress and safety. And 3. Autonomic reactivity follows a predictable hierarchical sequence of disinhibiting evolutionary neurocircuits in the service of survival.